A compass is an instrument used for navigation and orientation that shows direction relative to the geographic cardinal directions or points. Usually, a diagram called a compass rose shows the directions north, south, east, and west as abbreviated initials marked on the compass. When the compass is used, the rose can be aligned with the corresponding geographic directions, so, for example, the N mark on the rose really points to the north. Frequently, in addition to the rose or sometimes instead of it, angle markings in degrees are shown on the compass. North corresponds to 0 degrees, and the angles increase clockwise, so east is 90 degrees, south is 180, and west is 270. These numbers allow the compass to show azimuths or bearings, which are commonly stated in this notation. The magnetic compass was first invented as a device for divination as early as the Chinese Han Dynasty, and later adopted for navigation by the Song Dynasty Chinese during the 11th century. The use of a compass is recorded in Western Europe and in Persia around the early 13th century. Magnetic compass. The magnetic compass is the most familiar compass type. It functions as a pointer to magnetic north, the local magnetic meridian, because the magnetized needle at its heart aligns itself with the horizontal component of the Earth's magnetic field. The magnetic field exerts a torque on the needle, pulling one end pole of the needle approximately toward the Earth's north magnetic pole, and pulling the other toward the south magnetic pole. The needle is mounted on a low-friction pivot point. In better compasses, a dual bearing, so it can turn easily. When the compass is held level, the needle turns until, after a few seconds to allow oscillations to die out, it settles into its equilibrium orientation. In navigation, directions on maps are usually expressed with reference to geographical or true north, the direction toward the geographical North Pole, the rotation axis of the Earth, depending on where the compass is located on the surface of the Earth. The angle between true north and magnetic north, called magnetic declination, can vary widely with geographic location. The local magnetic declination is given on most maps to allow the map to be oriented with a compass parallel to true north. The Earth's magnetic fields are constantly changing, which is referred to as geomagnetic secular variation. The effect of this means a map with the latest declination information should be used. Some magnetic compasses include means to manually compensate for the magnetic declination, so that the compass shows true directions. History. The first compasses in ancient Han Dynasty China were made of lodestone, and naturally magnetized, or of iron. The compass was later used for navigation during the Song Dynasty of the 11th century. Later compasses were made of iron needles, magnetized by striking them with a lodestone. Dry compasses began to appear around 1300 in medieval Europe. This was supplanted in the early 20th century by the liquid-filled magnetic compass. Modern compasses. Magnetic compass. Modern compasses usually use a magnetized needle or dial inside a capsule completely filled with a liquid, while older designs commonly incorporated a flexible rubber diaphragm or airspace inside the capsule to allow for volume changes caused by temperature or altitude. Some modern liquid compasses utilize smaller housings and/or flexible capsule materials to accomplish the same result. The liquid inside the capsule serves to damp the movement of the needle, reducing oscillation time and increasing stability. Key points on the compass, including the north end of the needle, are often marked with phosphorescent, photoluminescent, or self-luminous materials to enable the compass to be read at night or in poor light, as the compass-fill liquid is non-compressible under pressure. Many ordinary liquid-filled compasses will operate accurately underwater to considerable depths. Many modern compasses incorporate a baseplate and protractor tool, and are referred to variously as orienteering, baseplate, map compass, or protractor designs. This type of compass compass uses a separate magnetized needle inside a rotating capsule, an orienting box, or gate for aligning the needle with magnetic north, a transparent base containing map orienting lines, and a bezel marked in degrees or other units of angular measurement. The capsule is mounted in a transparent base plate containing a direction of travel indicator for use in taking bearings directly from a map. Other features found on modern orienteering compasses are map and Roma scales for measuring distances and plotting positions on maps, luminous markings on the face of bezels, various sighting mechanisms for taking bearings of distant objects with greater precision, global needles for use in differing hemispheres, adjustable declination for obtaining instant true bearings without resort to arithmetic, and devices such as inclinometers for measuring gradients. The sport of orienteering has also resulted in the development of models with extremely fast settling and stable needles for optimal use with a topographic map, a land navigation technique known as terrain association. The military forces of a few nations, notably the United States Army, continue to issue field compasses with magnetized compass dials or cards instead of needles. A magnetic card compass is usually equipped with an optical, lensatic, or prismatic sight, which allows the user to read the bearing or azimuth off the compass card while simultaneously aligning the compass with the objective. Magnetic card compass designs normally require a separate protractor tool in order to take bearings directly from a map. The U.S. M1950 military lensatic compass does not use a liquid-filled capsule as a damping mechanism, but rather electromagnetic induction to control oscillation of its magnetized card. A deep well design is used to allow the compass to be used globally with a card tilt of up to 8 degrees without impairing accuracy, as induction forces provide less damping than fluid-filled designs. A needle lock is fitted to the compass to reduce wear, operated by the folding action of the rear sight lens holder. The use of air-filled induction compasses has declined over the years, as they may become inoperative or inaccurate in freezing temperatures or extremely humid environments due to condensation or water ingress. Some military compasses, like the U.S. M1950 military lensatic compass, the Silver 4B Militaire, and the Suunto M5N, contain the radioactive material tritium and a combination of phosphors. The U.S. M1950, equipped with self-luminous lighting, contains 120 mCi of tritium. The purpose of the tritium and phosphors is to provide illumination for the compass via radioluminescent tritium illumination, which does not require the compass to be recharged by sunlight or artificial light. However, tritium has a half-life of only about 12 years, so a compass that contains 120 mCi of tritium when new will contain only 60 when it is 12 years old, 30 when it is 24 years old, and so on. Consequently, the illumination of the display will fade. Mariners' compasses can have 2 or more magnets permanently attached to a compass card, which moves freely on a pivot. A lubber line, which can be a marking on the compass bowl or a small fixed needle, indicates the ship's heading on the compass card. Traditionally, the card is divided into 32 points, although modern compasses are marked in degrees rather than cardinal points. The glass-covered box contains a suspended gimbal within a binnacle. This preserves the horizontal position. Thumb compass. A thumb compass is a type of compass commonly used in orienteering, a sport in which map reading and terrain association are paramount. Consequently, most thumb compasses have minimal or no degree markings at all, and are normally used only to orient the map to magnetic north. Thumb compasses are also often transparent so that an orienteer can hold a map in the hand with the compass and see the map through the compass. Gyrocompass. A gyrocompass is similar to a gyroscope. It is a non-magnetic compass that finds true north by using a fast spinning wheel and friction forces in order to exploit the rotation of the Earth. Gyrocompasses are widely used on ships. They have two main advantages over magnetic compasses. They find true north, i.e., the direction of Earth's rotational axis, as opposed to magnetic north. They are not affected by ferromagnetic metal in a ship's hull. Large ships typically rely on a gyrocompass, using the magnetic compass only as a backup. Increasingly, electronic flux gauge compasses are used on smaller vessels. However, magnetic compasses are still widely in use as they can be small, use simple reliable technology, are comparatively cheap, often easier to use than GPS, require no energy supply, and unlike GPS, are not affected by objects, e.g., trees, that can block the reception of electronic signals. Solid-state compasses. Small compasses found in clocks, mobile phones, and other electronic devices are solid-state compasses, usually built out of 2 or 3 magnetic field sensors that provide data for a microprocessor. The correct heading relative to the compass is calculated using trigonometry. Often, the device is a discrete component which outputs either a digital or analog signal proportional to its orientation. This signal is interpreted by a controller, a microprocessor, and used either internally or sent to a display unit. The sensor uses highly calibrated internal electronics to measure the response of the device to the Earth's magnetic field. GPS receivers used as compasses. GPS receivers using 2 or more antennae mounted separately and blending the data with an inertial motion unit can now achieve 0.02 degrees in heading accuracy and have startup times in seconds rather than hours. For gyrocompass systems, the devices accurately determine the positions of the antennae on the Earth, from which the cardinal directions can be calculated. Manufactured primarily for maritime and aviation applications, they can also detect pitch and roll of ships. Small, portable GPS receivers with only a single antenna can also determine directions if they are being moved, even if only at walking pace, by accurately determining its position on the Earth at times a few seconds apart. The device can calculate its speed and the true bearing of its direction of motion. Frequently, it is preferable to measure the direction in which a vehicle is actually moving, rather than its heading, i.e., the direction in which its nose is pointing. These directions may be different if there is a crosswind or tidal current. GPS compasses share the main advantages of gyrocompasses. They determine true north, as opposed to magnetic north, and they are unaffected by perturbations of the Earth's magnetic field. Additionally, compared with gyrocompasses, they are much cheaper. They work better in polar regions. They are less prone to be affected by mechanical vibration, and they can be initialized far more quickly. However, they depend on the functioning of and communication with the GPS satellites, which might be disrupted by an electronic attack or by the effects of a severe solar storm. Gyrocompasses remain in use for military purposes, but have been largely superseded by GPS compasses, with magnetic backups in civilian contexts. Specialty compasses. Apart from navigational compasses, other specialty compasses have also been designed to accommodate specific uses. These include Qibla compass, which is used by Muslims to show the direction to Mecca for prayers; optical or prismatic hand-bearing compass, most often used by surveyors, but also by cave explorers, foresters, and geologists. These compasses generally use a liquid-damped capsule and magnetized floating compass dial with an integral optical sight, often fitted with built-in photoluminescent or battery-powered illumination. Using the optical sight, such compasses can be read with extreme accuracy when taking bearings to an object, often to fractions of a degree. Most of these compasses are designed for heavy-duty use, with high-quality needles and jeweled bearings, and many are fitted for tripod mounting for additional accuracy. Trough compasses, mounted in a rectangular box whose length was often several times its width, date back several centuries. They were used for land surveying, particularly with plane tables. Limitations of the magnetic compass. The magnetic compass is very reliable at moderate latitudes, but in geographic regions near the Earth's magnetic poles it becomes unusable. As the compass is moved closer to one of the magnetic poles, the magnetic declination, the difference between the direction to geographical north and magnetic north, becomes greater and greater. At some point close to the magnetic pole, the compass will not indicate any particular direction but will begin to drift. Also, the needle starts to point up or down when getting closer to the poles, because of the so-called magnetic inclination. Cheap compasses with bad bearings may get stuck because of this and therefore indicate a wrong direction. Magnetic compasses are influenced by any fields other than Earth's. Local environments may contain magnetic mineral deposits and artificial sources such as MRIs, large iron or steel bodies. Electrical engines are strong permanent magnets. Any electrically conductive body produces its own magnetic field when it is carrying an electric current. Magnetic compasses are prone to errors in the neighborhood of such bodies. Some compasses include magnets which can be adjusted to compensate for external magnetic fields, making the compass more reliable and accurate. A compass is also subject to errors when the compass is accelerated or decelerated in an airplane or automobile, depending on which of the Earth's hemispheres the compass is located and if the force is acceleration or deceleration, the compass will increase or decrease the indicated heading. Compasses that include compensating magnets are especially prone to these errors, since accelerations tilt the needle, bringing it closer or further from the magnets. Another error of the mechanical compass is turning error. When one turns from a heading of east or west, the compass will lag behind the turn or lead ahead of the turn. Magnetometers and substitutes such as gyro compasses are more stable in such situations. Using a magnetic compass. A magnetic compass points to magnetic North Pole, which is approximately 1,000 miles from the true geographic North Pole. A magnetic compass's user can determine true north by finding the magnetic north and then correcting for variation and deviation. Variation is defined as the angle between the direction of true north and the direction of the meridian between the magnetic poles. Variation values for most of the oceans had been calculated and published by 1914. Deviation refers to the response of the compass to local magnetic fields caused by the presence of iron and electric currents. One can partly compensate for these by careful location of the compass and the placement of compensating magnets under the compass itself. Mariners have long known that these measures do not completely cancel deviation. Hence, they performed an additional step by measuring the compass bearing of a landmark with a known magnetic bearing. They then pointed the ship to the next compass point and measured again, graphing the results. In this way, correction tables could be created, which would be consulted when compasses were used when traveling in those locations. Mariners are concerned about very accurate measurements. However, casual users need not be concerned with differences between magnetic and true north. except in areas of extreme magnetic declination variance. This is enough to protect from walking in a substantially different direction than expected over short distances, provided the terrain is fairly flat and visibility is not impaired. By carefully recording distances and magnetic bearings traveled, one can plot a course and return to one's starting point using the compass alone. Compass navigation in conjunction with a map requires a different method. To take a map bearing a true bearing to a destination with a protractor compass, the edge of the compass is placed on the map so that it connects the current location with the desired destination. The orienting lines in the base of the compass dial are then rotated to align with actual or true north by aligning them with the marked line of longitude, ignoring the compass needle entirely. The resulting true bearing, a map bearing, may then be read at the degree indicator, a direction of travel line, which may be followed as an azimuth to the destination. If a magnetic north bearing, a compass bearing, is desired, the compass must be adjusted by the amount of magnetic declination before using the bearing so that both map and compass are in agreement. In the given example, the large mountain in the second photo was selected as the target destination on the map. Some compasses allow the scale to be adjusted to compensate for the local magnetic declination. If adjusted correctly, the compass will give the true bearing instead of the magnetic bearing. The modern handheld protractor compass always has an additional direction of travel arrow or indicator inscribed on the base plate to check one's progress along a course or azimuth, or to ensure that the object in view is indeed the destination. A new compass reading may be taken to the target if visible. After pointing the dot arrow on the base plate at the target, the compass is oriented so that the needle is superimposed over the orienting arrow in the capsule. The resulting bearing indicated is the magnetic bearing to the target. Again, if one is using true or map bearings, and the compass does not have preset, pre-adjusted declination, one must additionally add a subtract magnetic declination to convert the magnetic bearing into a true bearing. The exact value of the magnetic declination is place-dependent and varies over time, though declination is frequently given on the map itself or obtainable online from various sites. If the hiker has been following the correct path, the compass's corrected indicated bearing should closely correspond to the true bearing previously obtained from the map. A compass should be laid down on a level surface so that the needle only rests or hangs on the bearing fused to the compass casing. If used at a tilt, the needle might touch the casing on the compass and not move freely, hence not pointing to the magnetic north accurately, giving a faulty reading. To see if the needle is well leveled, look closely at the needle, and tilt it slightly to see if the needle is swaying side to side freely and the needle is not contacting the casing of the compass. If the needle tilts to one direction, tilt the compass slightly and gently to the opposing direction until the compass needle is horizontal, lengthwise. Items to avoid around compasses are magnets of any kind and any electronics. Magnetic fields from electronics can easily disrupt the needle, preventing it from aligning with the Earth's magnetic fields, causing inaccurate readings. The Earth's natural magnetic forces are considerably weak, measuring at 0.5 Gaussian magnetic fields from household electronics can easily exceed it, overpowering the compass needle. Exposure to strong magnets or magnetic interference can sometimes cause the magnetic poles of the compass needle to differ or even reverse. Avoid iron-rich deposits when using a compass. For example, certain rocks which contain magnetic minerals, like magnetite, This is often indicated by a rock with a surface which is dark and has a metallic luster. Not all magnetic mineral-bearing rocks have this indication. To see if a rock or an area is causing interference on a compass, get out of the area and see if the needle on the compass moves. If it does, it means that the area a rock the compass was previously at is causing interference and should be avoided.